Listen-only mode.
Hello, everyone. My name is Terry Erzman. I'm the Vice President of Marketing for Citus Data. Welcome to today's webinar. Before we get started, quickly, I want to make sure everyone can hear us. So if you can hear us, please raise your hand in the GoToWebinar control panel. And I see lots of raised hands. Thanks, everyone. Appreciate it. As we go along, please, if you have any questions, enter them in the dialog box on the GoToWebinar control panel, and we'll go ahead and answer as many of those as we can at the end of the webinar. We are making a recording of today's webinar, so we'll send a link with the recording of the webinar as well as a link to the slides from today's webinar within the next 24 hours after we complete today's session. So please look for that in your email inbox. Feel free to share that with others. If there are any questions we don't get to today, because we have more questions than we have time, I'll pass those on to Marco, and we may be doing an additional blog post to answer any of those if we have some more topics to cover. With that, I would like to turn the controls over to Marco, who is a software engineer here at Citus Data, and he will be presenting today on Columnar store for Postgres using CStore FDW. Marco?
Thank you, Terry. Hello, everyone. So yeah, I'm a software engineer at Citus Data, and I work on our three main projects, namely PGShard, which is our open source extension for transparently sharding a table across many machines, CitusDB, which is our solution for parallelizing queries across a sharded table across many machines, and CStore, which is our Columnar store extension for PostgreSQL. And today we'll start with a short introduction of CStore for new users. So if you've used CStore before, this part is probably not going to be super interesting, but then we'll dive into some, very specific technical details of CStore. Look at the storage format. How does CStore lay data out on disk? How does it index the data to avoid reading, doing redundant reading? And how does it process queries? And we'll look at some performance numbers and compression numbers that result from that implementation. And we'll look at some more advanced uses of CStore FDW, such as compressing JSONB fields, and also some new features that are coming up in 9.5, which allows us to make tables which are both row-based and columnar-based, which is very cool. And I'll want to show a live demo of that. So to begin with the basics, like what is columnar storage? Probably most people know, but a regular table is typically stored row by row by row. So first you get the first value in the first row, second value, third value, and then the second row, and so on. And this is great for operations where you're selecting a small, relatively small number of tuples. And it also works very well for data ingestion, where you can just keep appending to the end of this table. Columnar storage differs from that in that all the values in a column are put together on disk. And this works very well if you have operations on a small number of columns, as in you have many columns, maybe 20 or 30, and your queries only hit one or two of them. And there's even cases when people want to use thousands of columns and only query a few of those columns. And then row-based storage becomes quite poor, because row-based storage sort of always forces you to read the entire row for all the relevant rows. And it's one added benefit of column storage is that because you end up often having a lot of very similar values next to each other, this type of data compresses quite well. There's a cost to that. I mean, you can already kind of see it from the picture. There's three different places where your data needs to go when you insert data into a column store, and then you also need to compress it. So there are certain trade-offs between row-based storage and columnar storage. CStore FDW is an open source extension for Postgres that provides columnar storage through the foreign data wrapper APIs, and also gives you compression of the data. It's available on GitHub if you want to If you have issues with it, please post them on GitHub, or if you want to send in patches or just do feature requests, please go to the GitHub and share your thoughts. So it's in a way it's not so much a foreign data wrapper as it more of an alternative storage format for Postgres. And the format is based on ORC files, which means optimized row columnar format, which comes from the Hadoop world. But it's not precisely compatible with that format, so it's not a foreign data wrapper for ORC files. And it is meant for append-only data. You can either copy data into it or insert into and then select from another table, but you cannot do individual inserts or updates or deletes on CStore. So keep that in mind. And the ORC file format is very much optimized for this type of workload. And one of the nice features is it automatically builds a sort of an index to skip over certain blocks of data when it's reading data. And this is very useful because being a foreign table, a lot of the index machinery in Postgres doesn't work for foreign tables, but CStore has its own index machinery. So what are the pros and cons of CStore versus a regular table? Well, especially what it's good at is reducing the amount of I/O that you do for queries that only use a small percentage of the columns, a small number of columns compared to a very large table. But it's okay if those queries hit many rows. It also lets you save on storage space if you compress your column data quite a lot, usually starting at 50% saving, but sometimes 90% or more. And kind of a side effect of data taking up less space on disk is that actually in memory it also takes up less space, so you can fit a lot more data in memory. Now you will have the computational overhead of decompressing this data. You cannot update, delete, or insert individual rows. I mean, it's inherently columnar stores are not so great at row-based operations. And indexes are only effective on sorted columns, which we'll get to later. And kind of a more theoretical, from a theoretical standpoint, columnar stores have cheap projection and expensive selection, and regular tables kind of have it the other way around. Now, this is just a really beginner's guide to CStore. If you want to use CStore, well, depending on what type of operating system you have, there's one dependency, which is the protobuf library. This was just so it would be simpler for us to write the code for serializing certain data structures. But then you can get the code from GitHub, build it, and then this is the main point of this slide. You want to add it to the shared preload libraries in your PostgreSQL.conf because some of the features will not work unless you do this, and I often forget, so I wanted to call it out and then restart Postgres as well. To get started, there's two commands that you want to kind of run once: create extension CStore FTW, which activates CStore, and then create server CStore server foreign data wrapper. These are just kind of things you need to do for extensions and foreign data wrappers. They don't really have too much special meaning to CStore. And after that, you can create a CStore table by saying create foreign table, and then the table name, and then the columns, and then server CStore turf. And in the end, you have these options, and there you specify that you want compression. If you don't specify anything, the data will not be compressed. There's only one compression algorithm right now that you can use, which is PGLC, because that's the one that's built into PostgreSQL. After that, you can load data either by doing insert into events, select star from another table, or you can use copy events from a file with the right format. So both of those will work. And after that, you can just query the table as any other table. There's no restrictions. So what might you use this CStore for? Well, I think the main use case is actually analytics, where analytical queries tend to have to go over a lot of rows, but are often only interested in a few columns. So this is a very typical analytical query. Get the, it says get the revenue, I don't know why it says that, but it says this query actually gets the number of events by country over the year 2015. Now on a regular table, that would mean basically reading all of the data, all of the columns for all of the rows in 2015, and then just counting the countries, the number of events per country. Now, if we have a columnar table, we can just only read the country and the event date columns, because we need the event date for the filter and the country for the counting. And that could be, depending on how many columns there are, a big reduction in I/O. And a big reduction on I/O often means the query runs a lot faster. But I mean, if this is a table with just 2 columns, then it's probably not going to make a big difference. But typically there are a lot more columns. The other big use case is data archival. So there's not really a built-in compression mechanism in Postgres for regular tables. There's certainly toast, which is if you have big big values like big strings, they are stored more or less outside of your table and can be compressed, but no like general table compression mechanism. And it wouldn't even work well, because in a row-based table you get some ID, some timestamp, some value, and then other things, and then this doesn't compress well together compared to columnar store. And well, one of the things you could do, for example, is you could have a regular table, let's say an events table and an archive table, and with SQL you can quite simply copy data from your events table into your archive table. I'll show you an example of doing this later in a kind of a safe way as well. And yeah, I'll also show you some compression numbers of like this could save you a lot on storage space and still make your data queryable as if it was still in the regular table. Now the data format used by CStore is inspired by the optimized row columnar format that was developed by Facebook and Hortonworks. And there's a few concepts which are kind of relevant to know about if you're, trying to tune CStore, for example. Basically, CStore stores tables in 2 files. One is the data file and one is the footer file. And the data file contains what we call stripes. And then these are just blocks of ranges of data. And stripes contain blocks and metadata on blocks for each column, and I'll get into more examples of this. And then a block contains a null bitmap and then the actual data in possibly compressed form. So it's important to know that each time you do a copy or an insert into select, you create a new stripe, and a stripe has certain metadata on where the blocks are in the stripe, for example. So what you don't want to do with CStore is, do very small copies over and over and over again, because you are going to have a lot of stripes with a lot of metadata, which is not going to be super efficient. You want to try to, as much as possible, ingest data in bulk. Another important thing to know about stripes is that they are buffered in memory. So when I'll discuss query processing later, but when CStore reads data, it kind of has to read ahead because it wants to read column by column, but Postgres is asking for the data row by row. So it has to read a whole bunch of rows in advance and then basically return them to Postgres row by row. And the unit in which it reads ahead is a stripe. Now, the sizes of stripes is configurable. So if you see CStore using a lot of memory, you might want to make your stripes smaller. So zooming into the data format a bit more, there's a data file which contains stripes. And by default, a stripe contains data for up to 150,000 rows. But you can make this more or less depending on your memory requirements. Then at the start of a stripe, so this is just blocks a stripe is a big block of bytes, essentially. At the start of that stripe, you'll find the skip indexes. So these are not things you need to know, but this is like, or to use CStore, but this is just to get an intuition for how CStore actually works. The skip indexes contain min and max values for each of the blocks. Then after the skip indexes, then there is a section for each column in the table. And for each column, there will be a number of blocks. And a block contains data for up to 10,000 rows, also configurable. And as I said, the block consists of an exists bitmap, which says whether or not a value is null, and then a large sequence of PostgreSQL datums, possibly in compressed form. And just the fact that it uses PostgreSQL datums also lets you pretty much use any data type you want within a CStore table. At the end of the stripe, you'll find the stripe footer, which just contains a bunch of offsets and lengths for each entry in the skip index and for each block. Not very important. What is somewhat important to know is that separately there is a footer file, and that contains the offsets and the lengths for each stripe. And we'll get back to why that is important. But basically, by reading the footer file, CStore knows what's in the data or where the stripes are in the data file, or where the stripe footers are in the data file, and then it reads the stripe footer and it can read the stripe. Okay, so that gives us some basic idea. Here it is in a picture. This is actually a picture of the ORC format, but it's exactly the same for CStore. So you see here, there are actually 3 stripes, and then the footer, and the stripe starts with index data. Oh, that was not my intention. The stripe starts with index data, which contains min and max entry for each block, and then row data, which contains for each column the actual blocks of data. Okay. So what are these skip indexes with these min and max values? Well, for each block of data, CStore actually keeps track of what is the minimum value in this block that has been ingested and what is the maximum value. And then at query time, it checks whether, it looks at the where clause and checks whether the expression that the value of the column is going to be between min and max is never going to be true given the where clause. So for the query that the user is making, none of the data in this block could possibly make, all of the data in this block will be filtered out. We know that from the min and the max value. And there's some internal Postgres functions, in this case predicate refuted by, that do this for us. We didn't even have to write code for this. And this works especially well if you have sorted data, like, for example, time series data, where you have every time you add new data, like the timestamps are higher and higher and higher. So in this example on the screen, then there might be a block 1, which with 10,000 rows, which go from the 1st of December to the 31st of December 2014, and then another block which contains 1st of January to 31st of January. It's usually not that nicely aligned, but and then if you were to make a query for a date that is like where the event date is at least the 1st of January 2015, CStore knows it doesn't have to read the first block. And it doesn't have to read the first block for any of the columns, because remember, we like for each column we have, let's say 10 or 15 blocks in a stripe. But if the skip indexes say for any of them that, okay, this could never be true given the where clause, the value could never be between this min and max, then that block is skipped. So this is kind of almost pseudocode for the actual implementation of CStore. If you go to the source code, you'll more or less find this this overview. So the foreign data wrapper API has a couple of functions. One of them is begin, that sort of the implementer has to do, or that the extension has to implement. One of them is the begin foreign scan, and when a user does a select query, then well, first Postgres will call the begin foreign scan method of the foreign data wrapper, and then it will keep asking for rows through the iterate foreign scan, and finally there's an end foreign scan. So what CStore does with this API is in the begin foreign scan, it reads the table footer. So this is the separate file which tells us what exactly is in the data file. Then whenever Postgres asks for another row from this foreign table, then CStore checks, well, do I have any stripe buffered in memory? If not, well, I look at my table footer, find the next stripe, read the stripe metadata, read the indexes, use the indexes to find blocks that I can skip because I know they would never match the where clause. And then I read the blocks that I cannot skip, but only for those columns that were in the projection. So the where clause and the projection are both provided via the foreign data wrapper API. So CStore knows about these. And projection is basically just the list of columns that are used in the query. So it only ends up reading the columns that are in the query, and it only reads the blocks of data which are not refuted by the where clause. So the next step, it looks at, is the current block, so let's say the first block, if it's not yet been deserialized, because at this point the whole stripe is in memory, but it's still compressed. Now, and then it actually looks at a block. If it's not been deserialized, it decompresses it and deserializes it. Well, that's sort of one step, really. And so then also we have the uncompressed data for one block in memory. And then we return a tuple from that block. And then PostgreSQL does the rest of its query processing magic. And so it's important to remember, well, while processing a query, CStore keeps a stripe in memory, but also one uncompressed block. And that's why you might want to change the size of your block if an uncompressed block takes up too much memory. So these are things to be aware of if you're tuning a CStore FTW table. Now, a thing about foreign tables is that if you write your regular table, you go to it first goes into the write ahead log, and then if there's a crash, if Postgres crashes, and then starts up again, it first reads the write ahead log to see what happened just before the crash. And it's okay if the write ahead log gets truncated in a way; it doesn't cause anything to break. But writes to a foreign table don't go to the write-ahead log. So what happens if a crash occurs? Well, if you write to a CStore table, then first you will start appending to the end of the data file. So you'll add a new stripe, basically. But only at the very last step is the footer file, which contains the position of the stripe in the data file, updated. So as long as the footer file has not been updated, the data is not yet visible to new queries. So if you do have a crash, what you will have is there will be some redundant, useless data at the end of your data file that is not referenced anywhere in the footer. So what happens if you write again? You will just simply overwrite that data. So nothing. I mean, you will lose your data, or you will lose that write if Postgres crashes, obviously, but it doesn't get CStore into a bad state because only once, like when the write commits or when the write completes, then it overwrites the footer file, and this is an atomic step because it puts out a temporary file and then overwrites and then renames it to the footer file, and this is atomic. So the footer file can never get truncated if there is a crash. But there are certain implications of this model, which is when you do backups. So if you want to do a backup of a CStore table, there are, you can use some of the common techniques. Again, like CStore writes to a CStore table do not go through the wall log. And for example, streaming replication is based on copying the vol log. So you don't, if you use streaming replication, writes to a CStore table will not show up on the secondary. But a common technique you can use for backing up a C-store table is just doing pg dump or just even copy from to get the data from the table. You can also make a file system level backup. If you shut down the database, you can just copy the database directory because by default C-store places the data and the footer files in the database directory. Alternatively, you could also just take the actual C-store files. I mean, there's only 2 for each table. So if you look in the database directory, you'll find a C-store FTW directory. Then there's a database directory for each database, and then for each table, there's 2 files. If you do this, make sure you copy the footer file first, because it's okay to have an older footer file and a newer data file. So then the data file might have some data that's not in the footer, but that's okay. But it's not okay to have some data reference in the footer that's not in the data file. That in that case, your table will break. Now, if you've copied those files somewhere, then you can recover these by when you create the foreign table, you can specify a file name. Note that when you do this, you are going to also write to that file again. So you don't want to point it directly to your backup, basically. But I mean, most commonly, I think people just tend to use SQL level backups, but you could also copy around the files, or even use that for replication or other types of tasks. So compression. The compression algorithm used by C-store is PGLC, because that's what's included in Postgres, and Postgres uses that for things like Toast. And I think also in newer versions to compress the wall log itself. And now what type of compression ratio you get out of that depends a lot on your data, how it's structured, is it sorted. For compression, ideally you want a lot of very similar values appearing one after the other. That compresses really well. But for the TPCH, which is this analytical benchmark, which also lets you sort of generate a somewhat random data set of any given size, we see about a 4x, so about a 75% reduction in storage space. And interestingly, even if you do not use compression, with C-store you tend to get some reduction in storage space just because the ORC format is very compact. What can also compress quite well in certain cases is if you have JSONB columns. A problem with JSONB is that every object in your database will have the same field names over and over again. So we did some experiments with, for example, the customer reviews data set that you'll find on the Citus data website. And there we can easily compress the data by more than 6 times. But you know, there's also some noisier data sets, like there's the GitHub events archive, where all the events on GitHub repositories are logged. And these are all very different events with all different fields and big commit messages in them. And so then the compression might not work as well. So it depends a lot on the data. And you can sometimes get a lot better compression simply by sorting your data on a certain column such that all the similar values are similarly next to each other. In terms of performance, C-store tends to work very well, especially if you're a little I/O bound, because that's where you get the real gain out of not having to read everything. So the TPCH benchmark has a bunch of interesting join queries which go through a lot of several tables and have to read most of the data. And then we see for regular compared to C-store, then there's often a 50% lower query times when you're dealing with uncached data. So it's actually reading data from disk. And so the benefit here is greatest if you use compression, because that means even less data to read from disk, in addition to just having only reading the relevant columns. The rightmost bars here, I don't have a label, unfortunately, but that is just a select count star from line item, which is the biggest table. So this is a very simple query which has basically a minimal amount of computation and it's basically just I/O. So in that case, you can see there's a huge difference between using CStore and using a regular table. These are the same queries, but then on SSDs. Now here the effect is a bit less profound because SSDs are quite fast. So in this case, I/O is not so much a bottleneck, but you can still get pretty good gains. Just query 14 is still like twice as fast, but some of them are more in the 10 to 20% range. But if you have simpler, so most of these queries are actually pretty complicated joins. If you have simpler queries which are more I/O bound, then the effect of CStore will actually be bigger. This is for these queries just how much I/O is actually done, how much data is read from disk for, again, regular table CStore and compressed. And this nicely shows the difference. Well, going from blue to red is basically the effect of only reading certain columns, and then from red to orange is the effect of compression. So there's and this will, I mean, these numbers are somewhat important as well if you have multiple queries running at the same time. And this is just a very, an empty system where there's only one query being run at a time. But if you have multiple queries contending for the disk, this could make a huge difference. Now, also to be fair, if you have a pretty much in-memory workload, so all your data is cached in memory, then especially in the compressed case of CStore, you will start to notice there is the cost of decompression, basically. Because here you've lost most of the I/O benefit. I mean, reading data from memory is pretty fast. But now, if you've compressed your data, you certainly need to pay the price for decompression. So in this case, CStore might not be faster. If you have a sort of small data set that just easily fits in memory, CStore might actually be slower. But actually, in all these cases, when you're not using compression, it's still faster because there is less data to read from memory. But be aware that you might not, if you have a relatively small data set, you might not actually see benefit, even if you do very heavily analytical queries. So a more advanced use of CStore is combining it with JSONB. As I said before, actually, the JSONB is huge. I mean, it's efficient in comparison to the JSON format, but compared to like relational tables, at the very least, it takes up a lot of storage space. So here you see in the graph, you see some examples of our customer reviews data set. What happens if you just load it into kind of relational table? It's about 138 megabytes. But then a CStore table is only several times smaller. But the JSONB form of that same data is about more than 300 megabytes. And so this is quite a big cost. But you can bring that back down to 50 megabytes, so more than 6 times reduction by putting it into a CStore table. Now, you will lose some benefits if you do this, like being able to like GIN indexes on certain JSONB fields. So there could be use cases where this really helps, and some which it might make everything a lot worse, except for storage space. Certainly for archival of JSONB, this is, I think CStore is a great solution. It does depend on the structure of the data. It's not like every JSONB object or every table with JSONB objects will compress well, such as the GitHub events. You'd expect it to be more like 2 times smaller by using CStore. Another kind of really cool feature that we'll get in Postgres 9.5 is foreign table inheritance. So the current release of CStore, I have to admit, is not compatible with 9.5, but if you go to GitHub, there is a branch that is compatible with 9.5. We're aiming for the next release of CStore to be backwards compatible as well with 9.3 and 9.4. So table inheritance lets you basically create a parent table and then child tables. And when you query the parent table, you will see all the results from the children as well, which so far was kind of useful because you could do partitioning. You could put some parts of your data on a different disk, for example, which is very useful. But in 9.5, that same technique will also work for foreign tables. And then we can do all sorts of interesting things. And for CStore, one of the things we can do is create a table that is part row-based and part columnar. So then some of the drawbacks of CStore, such as not being able to do individual inserts, actually go away because we can just insert into the row-based table. And we can periodically just take data from the row-based table and then just move it into the CStore table in bulk to get good compression and better analytics performance. And then I can query both as if they were one big table via the parent. It actually says inherits main in the SQL. This should be inherits events. Now, I want to actually demo this feature because I think it's pretty neat. So I'm going to go to my my console. I'm actually thinking maybe I can make this a bit bigger. Let me just check if I can. Okay. That didn't help much. 14. No, it doesn't actually do that. Well, okay, we'll work with this. So this is just a Postgres server running on my desktop, and there's a couple of tables here. You can see the JSONB tables. Well, I can show you the numbers, but they're similar to what's on the slides. I wanted to focus on the events tables. So you can see there's one events table, which is the parent table, and then there are several foreign tables, which are actually CStore tables. One for the first three, each of the first 3 months of 2015. And then there's an events current table. So this is the row-based table. And this currently actually contains data for April, May, and June of 2015, so the second quarter of 2015. In a bit more detail, this is the actual SQL I used. So I used the GDELT data set, which is a publicly available data set published by Google. Which contains events, just basically news events that happen around the world that they, I guess, automatically extract from all sorts of news organizations. And it contains all sorts of metadata on those events, like well, when it happened, who the actors are, where they are located, how many times this event was mentioned, and in how many articles. It gives you a URL. And so there's actually a lot of columns in this data set. And so the way we're going to store this data set is there's going to be a row-based table which contains the latest data, and we can put indexes on this table if we want. And there's going to be a couple of archive tables which contain the older data. And these are using CStore and with compression. And so we have one for January, February, March. And finally, I've put an trigger on the main table. So if I insert into events, the events table, it will actually go into the events current table. So this is really, this is a table I can do inserts on, but I'll also be able to do, columnar analytical queries on it in that sense. So yeah, I can show you a bit more about these tables. So the events table has 4 children, which are 3 CStore and 1 row-based. And this is one of the CStore tables. So for January, I've put a constraint on it such that if you query the events table with an event date that's in January, then or not in January actually, then it will not query the CStore table. I can show you the sizes, and those are quite interesting because the events current table contains about 15 million rows, and each of these tables contain about 5 million rows. So the number of rows between the columnar part and the row-based part is about the same. But as you can see from the sizes, here this takes up slightly over 1.5 gigabytes, whereas the row-based part with about the same number of rows takes up about 14 gigabytes. So that's about a factor 10 difference. So I can show you just querying the CStore tables by themselves without going through the parent. So this contains about 4.4 million. And what I want to show you is actually the use of skip list indexes. If I say something like event date equals 2015-01, let's say 01, then this query is going to be a lot faster, even though it's actually just, it's a similar query plan for both queries. It just doing a foreign scan. But when I specify the event date filter, it can actually use the skip indexes, which is very useful because it makes the query a lot faster. And actually in the explain pane, I can also see this is the size of the table, and I can see where it's located on disk. So this is quite useful. Another thing I can do, which is the point to foreign table inheritance, is actually query the main table. So I have a prepared query for that. Remember at the start, I showed you a query where we counted the number of events per country. So I can do that on this table where I can take the country, number of events, and then give me everything in the first quarter of the year. So between 1st of January and 31st of March. I apologize for this appalling way of representing dates, but that's how the GDELT dataset represents dates. And so it groups by country. So most events in the USA, probably because most news agencies are there, Britain, France. I can also do this for Q2, and Q2 is the, so it's going to be on the same table, on the events table, just a different date range. And well, the problem is Q2 is the row-based part of the table, and as I said, CStore is a lot better for analytics than a regular table. So this query is going to take, I know it's going to take about a minute or so. So I might actually just do something else while waiting for this. Because I also like to show you that you can just do, let me just do this. You can pretty much just insert into the events table, even though like you cannot directly insert an individual row into the CStore table. You can insert it into the row table, and I can now say, well, give me all the events from July onwards. Well, that's just the one I just inserted, and so this is the same table that my Columnar partitions are in. Let me see if my query finished. Okay, it took about 30 seconds this time, so that's good. So CStore in this case was about 5 times faster than just doing this query on row-based storage, just because of the nature of the query. There are other types of queries which will be a lot faster in the row-based case, such as looking up values on a particular field that is indexed, like the event ID. I might have a query for that. So if I query by a particular event ID, if I do that solely on the row-based table, then this is a really fast query. If I do it on the full table, then the CStore tables will also try to find this event. But the event ID also is able to use the skip list indexes quite well, so this is not an incredibly slow query. Now, the other thing I wanted to show you is data migration. So what we can do now is create a new partition, and I was planning to, just do the month of April, migrate that, until I realized that this amount of data on a single machine, it's going to take a minute or two to actually copy that much data and compress that much data, so that might not work well for a live demo. So I'm just going to do a single day, the 1st of April, 2015. So what I can do is I can create a new partition, and this inherits from the events table as well. And then I can take data from my events current table, which is my row-based table, which contains the second quarter. And then I take all the rows which are April 1st or before. I happen to know there's no rows from before April 1st. And I put that into my CStore table. So this query, I think, usually takes about 10 seconds because it's not that much data, but it's about 200,000 rows, actually. And if after doing this, I can see that if I do queries on my events table, it now also includes my new partition, and the data has been deleted from the row-based partition. So I've moved over the data from my row-based table into the CStore table, where it's now compressed, and based on the storage size numbers, I know it takes up 10 times less data, and queries run considerably faster. So this is a very neat feature that you get when you combine 9.5 foreign table inheritance with CStore, that you can kind of get the best of both worlds to some extent. So summarizing the webinar, we discussed, well, gave a brief introduction and then discussed CStore FTW internals. A few concepts to be aware of are stripes because they're cached in memory, blocks because they're decompressed in memory, and footers because that's how the metadata is kind of transactionally updated. There are skip indexes, which automatically index sorted columns. So this, you don't have to do anything for it, but it might be worth considering whether the data that you insert is actually sorted by a particular column that you want to query on. And we looked at query processing of, how CStore kind of reads a bunch of data ahead to make sure you only read particular columns and then buffers it in memory. And we saw some performance numbers and saw that it works really well for IO-bound workloads. If you have a purely in-memory workload, it doesn't generally provide as much benefit. And compression is often 50% or more. In the example we saw with the GDEL data set, it's actually close to 90%. And that's because there are actually a lot of columns in that table which are, for example, have no values or the same value over and over again. And so that compresses really well. And we did a demo where we saw that, some new features with 9.5 where we can actually combine row-based and columnar storage into one kind of view and get some of the best of both worlds. So that concludes the presentation part. So now we can get to questions. So over to Terry.
Okay, Marco, thank you. Let's see, first question we have is, does the append-only data need to be in a particular order for the automatic indexing to work?
Yes, because the order in which you insert the data or copy in the data is the order in which it will be appear in the blocks, and the ranges are computed per block. So if you have a mixture of very high and very low value in each block, let's say you have values from 0 to 100, then maybe each block will have maximum 100 and minimum 0, and then it's not very effective. But then if you sort by that column such that the first block ends up having 0 to 5 and the second block ends up having 6 to 10, then the skip indexes become effective. If you use the insert into select method, you can control this, right? Because you can specify that you want to order by a certain column. But yeah, the way you sort data, it matters for the effect that the skip indexes have.
Okay. Just a reminder for everyone, if you have questions, please put them in the questions box in the GoToWebinar control screen. Next question is it possible to populate the data with Scoop or generally from Hadoop?
Not directly, as in you just take a file and then turn it into a CStore table. I mean, you can just use any kind of format that is supported by the Postgres copy command, and you can also, if you need to do any sort of pre-processing, which means not strictly necessary, but you can use it you put it into a temporary table and then insert from that table. So yeah, there's no difference in that regard between a CStore table and a regular Postgres table in terms of migrating data.
Okay, next question. Does CStore use GPU for compression and analytics if PG-Strom is also installed?
That's an interesting question. I would think not, and that has to do with the well, the foreign data wrapper API is somewhat limited in terms of what it does at execution time. Pretty much, you always do a type of sequential scan on a foreign table, but then CStore internally actually avoids reading most of the data, so it doesn't actually do a full sequential scan. But there's no, at least not at the moment, you don't get like the execution of queries on foreign tables is pretty basic. Now, this is changing a bit. There are the foreign data wrapper API is getting more, let's say, access to the internal execution logic of Postgres. So potentially in the future, this could be added, but it's not currently.
Okay. Next question. Do these tables need to be vacuumed and or analyzed like regular tables?
Yes, they don't need to be vacuumed because it is append-only data. So vacuum is necessary because, for example, in Postgres, if you update a value, you will actually append the new value of the row to the end, and then mark the old value as no longer visible. And then at some point, you need to reclaim the space used by those updated values or deleted values. In CStore, this is pretty simple. There's no updates or deletes, so there's no space to reclaim. You will want to analyze your tables because there are some useful statistics that CStore provides to the Postgres planner that it can use when it does joins, and this especially it always wants to figure out is if I join two tables and one of them is large and one of them is small, this might have an effect on the overall query plan. And so CStore can provide this information to the Postgres planner, but you want to run analyze to make sure you get that information.
All right. Next question is, can you provide any insights on using CStore with spatial data? Any experience or?
I have no personal experience with it. It's an interesting point. I mean, I would guess that the way PostGIS stores its data, it would be fairly straightforward to replace that with a CStore table. I think the interesting question is that a use case for which it works well, which is something that is worth sort of figuring out and benchmarking. Like it depends on are there a lot of compressible columns that compress well? If I'm thinking of, for example, coordinates tend to be long floating point numbers, for example, which have a lot of randomness to them, or apparent randomness, then that might not compress very well. But then if there are a lot of queries, if these are tables with a lot of columns and the actual queries that you do on them only use a few of those columns, then that might actually be a good use case for spatial data. So I'm not familiar enough with the specific PostGIS internals and data format to really answer that question, but it's a very interesting thought.
Okay, next question. For removing data, can we use delete and truncate?
No. So either you'll want to, pretty much if you want to delete data, you'll need to use replacement. So in the example, the demo I showed, we had a partition for every month. So at some point you can remove a partition, but you cannot delete directly from a table. So you could construct in a single transaction, for example, construct a new table from the old table where you copy part of the existing data into the new table and then drop the old table and rename the new table. That is something you could do, but there's no direct delete or truncate.
Okay. Next question. What's the best way to replicate CStore tables to other servers as they aren't replicated by Postgres?
The best way, that's an interesting question. So Well, one way we use a lot for, let's say, Citus data customers is with CitusDB, which also can use CStore because it's just pretty much regular Postgres. And CitusDB does its own replication. And what CitusDB does internally, it just copies over the CStore files, so first the footer file, then the data file, to a second replica node, basically. So, I mean, I think that approach is very simple and works well in that regard. Like there's no form of streaming replication. But I mean, doing this at the file level is very simple. But potentially, you could even have a type of rsync where you periodically copy over the footer and the backup file and the data file. Like, I mean, as I said, the main thing is to make sure that you copy the footer file before you copy the data file. But I think doing it at the file level it makes the most sense.
Okay, the next question is it possible, practical to move CStore tables between servers, create on one, later move to an online archive server, for example?
Yes, I mean, I think it's the more or less the same story that, yeah, you can do this. Like, it's a bit trickier, obviously, to copy it into a live database, because you need to keep the footer and the data file in sync somehow. But I mean, no, this is all. I mean, it's not super hard to get that done. But copying into an archive database yeah, that's very simple, because you just copy over the two files and then do a create foreign table and then specify the file name of the file that you copied over, and then you can just query everything as normal.
Okay. Are DDL commands like add column supported?
Yes, as of the latest release, I think 1.3, alter table, add column, and drop column are supported.
Okay. Are there any issues with chained FDW usage, such as using PostgreSQL FDW to access a CStore FDW on a remote server?
I wouldn't think so. It depends a bit. Like the foreign data wrapper APIs are changing a bit as well. I'm not intimately familiar with Postgres FDW, for example, of how whether it, for example, forwards DDL commands, and then whereas you're supposed to do alter foreign table, it actually does alter table, and then the alter table fails because it's a foreign table. I could imagine there are some issues. I haven't actually I haven't tried to figure this out. But most of those things are not actually currently supported by the FDW API, so to some extent that avoids the issue. But yeah, I mean, in principle, things like the simple things like querying, select queries, there will not be any issues of using Postgres FDW plus CStore FDW, or copies or inserts or those kind of things.
Okay. Very good. Well, thanks everyone. There were a few questions we didn't have a chance to get to today, but we're at the end of our time, so I'll pass those over to Marco, and if possible, if it makes sense, he may answer those in a blog post at a later time as well. Again, today's webinar was recorded, so we'll send a link to the webinar recording once it's posted online, as well as to the slides. Thank you all for attending, and please check back for future webinars, which will be posted to our website in the near future. Thanks, everyone. Have a good day.
Thanks.